Hi all, welcome back to Environmental Science 101. Last time out we talked about what constitutes or what gives trees their mass, okay, going from a couple gram seed to a tree that weighs tons. What kind of constitutes that exchange of mass over a period of time? And it was research that was done by John Baptist van Humboldt, that and his kind of famous experiment done on willow trees, that kind of shined a little bit of light that plants are not gaining mass, or not very much mass, from the soil that they're in. And sure, they might exchange nutrients, and they're going to take up nutrients and water from that soil, but they're going to exchange nutrients back. Their leaves are going to fall and decay in the soil, and they're going to add stuff back to it. And really, there's not much of a net change in the mass of the soil. So John Baptist suggested that it was the air. And so after his work, Jean Zinber, who was a pastor first and then became a naturalist and a botanist, he demonstrated early on that plants were able to absorb carbon dioxide, and in doing so, they'd absorb carbon dioxide and they release oxygen. And he did this in a pretty famous experiment also. He would raise plants in glass jars and light candles and do other things with matches and candles and plants inside a container to look at that transfer of carbon dioxide and release of oxygen. And he did this in the late 1700s. So after John Baptist's work, we had this kind of idea in this play that, hey, this is what's going on. And then from that, Julius Sachs did research in the mid-1800s that suggested how this whole process is kind of connected, and that chlorophyll, these little packets, little organelles inside the cell, inside plant cells, were absorbing sunlight, and they were the kind of the housing or the packaging plant for the production of sugars or starch. And that's where the carbon comes into play. The carbon dioxide is coming out of the atmosphere. The sunlight is the energy that's needed to repackage the carbon dioxide with oxygen and water, and then that's going to produce some version of a carbohydrate, some component of C6H12O6, and in doing so, you have these packages of energy, and those packages of energy can then further be repackaged as structural components, or they can be kept as a monosaccharide or a simple sugar like glucose and fructose and things like that. Okay, and so that early work by Julius and John and Jean Baptiste really kind of pointed to the connection of the sun with the atmosphere, with the carbon dioxide that was in the atmosphere, and that connection between the two, and kind of connecting how photosynthesis works. Okay? And of course, later on, we figured out all the enzymes and the proteins and the pathways and exactly what's involved in photosynthesis, and how certain things can hijack photosynthesis, like having too much oxygen in the system and things like that. And we'll talk more about photosynthesis in much greater detail as we progress. Okay, so now I kind of just want to review what matter and energy are, this is a pretty simple review. Most of you have had this before in kind of other science classes. But we have states of matter. We have a solid, liquid, gas, and then a plasma state. And as you add heat to most materials, you move from a solid state to a liquid state to a gas state to a plasma state. And so sometimes the heat that's coming from the sun is enough to do this. Okay, at least change some states of matter. Other times, the amount of heat that needs to be added either has to come from a man-made system or from things like, volcanoes or something like that. Okay. And energy, we'll talk a lot about energy because in environmental science, one of the huge components of environmental science is, where does our energy come from? How is this energy converted? How's this energy utilized? Do we have enough energy for the 8.2 billion people on the planet to all live like people in the United States, for example? And if we want everyone to live similar to the people of the United States, then what's the energy output got to be? How are we going to get there? We're going to get there with wind turbines and solar panels. We're going to get there by digging more fossil fuels out of the ground. Are we never going to get there? Are we going to get there by splitting atoms? How are we going to get there? And we'll talk about matter and energy from that perspective. Okay? So if we kind of combine the two things, photosynthesis, plant growth, matter and energy, we can get at kind of that transfer of matter or transfer of energy or both, and what's required in order for a plant to grow. Okay. So matter is any physical substance that has a mass and occupies space. Okay? And we still hold this definition true, even though as we progress with science, we start developing things that are a little bit borderline on this definition. For example, light has never been considered matter. Okay? And so, except for now, we have the capability of making solid light. So if you make solid light, therefore, the argument could be that it occupies space. If it's a solid, does it have mass? And so right now, the definition is still that light doesn't have mass. But if it's a solid, it occupies space. So it's not quite matter, but you start to get into a situation where our definitions don't fit what we can do in, say, a closed system. Okay, which is great because science. The nice thing about science is it can evolve, it can change. Our definitions can change to include things that we now can do that we never thought we could do when we developed a definition, like the definition of matter. Mass is a measurement of the amount of matter of an object. Okay? And so if an object has a mass, so like this beaker with this water that's in it, has a mass of 254.09 grams, then that's also the amount of matter of that object. Okay? And so often we're not technically interested in the matter piece. We're actually interested in the mass because it's easiest to measure. And we don't always know what the matter consists of. We don't know exactly what components are contributing to the mass. Even in the best systems that we know, we may not know all matter that contributes to the mass, but we can tell what the mass is. And you'll see what I'm talking about when we progress in the course. Volume is a measurement of the amount of space an object takes up. Okay? And so often we think about matter is the mass, okay, and the volume. Okay, so mass and volume equals matter. Again, like, we can measure volume. We can measure the space, the amount of space an object takes. Okay? And energy, a simple definition, is just the capacity to do work. We will come back because in environmental science we have kind of a definition of energy that we often work with. We have biological energy and then kind of chemical energy, and the two are related to each other, but they're a little bit different, and you'll see what I'm talking about here in a second. Okay, so if we go to some basic chemistry, okay, we can look at carbon atoms. Okay, so carbon atoms are important for living life forms. Okay, all living life forms are composed of carbon. Okay, so but when we look at a carbon, it has like a few components that you should probably know. It has a nucleus. Okay, don't think of this as the same thing as like a nucleus of a cell. Even though the two words are the same, they're not composed of the same material per se. Okay? The nucleus, the term nucleus just means center, or like center nut. And so it means the center of an object. And so in the case of an atom, that's composed of protons and neutrons. Okay? And so the protons will have positive charge and the neutrons have a neutral charge, or no charge at all. Okay? And then orbiting or surrounding this are electrons. And from a chemical and kind of chemistry, physical definition, electrons are energy. Okay? And even in biology it is, okay, because all of our stored energy eventually have a role, a chemical energy, where electrons are being released and then combined to, drive work in some way. Okay, but often when we talk about energy, we talk about energy from an electron perspective, and then energy from something like an ATP or adenosine triphosphate perspective, and we'll talk about this as we progress. Okay, so all matter in the universe is made of atoms. Okay, and this is another reason why light is not considered matter, because light is made of photons and it's not an atom. Okay, but all matter in the universe is made of atoms, the smallest particle that still exhibits the characteristic of its element. Okay, and so we'll briefly kind of cover this, but again, like I just said, protons have positive charge located in the nucleus. Okay, it determines the atom's elemental identity. So you change the number of protons, you change what atom you are dealing with. Okay, so if we have one proton, okay, we're dealing with hydrogen. Okay, if we change that to 2 protons, we're dealing with helium. Okay, and so anytime you change the protons, you change the element's identity. Okay, you can change the number of neutrons though. So neutrons, we'll talk about electrons first. Okay, so electrons are negatively charged, orbit the nucleus, and really the interesting thing about electrons is they're what gives that atom its activity level, or kind of predicts its behavior. So if that atom is going to bind to other atoms, it's due to these electrons. Okay, if that atom is going to kind of reject things, or is likely to not be very reactive, then it's due to typically the lack of electrons. Okay. Neutrons, again, are neutral. And like I was just about to say, is you can change the number of neutrons. Okay, that changes the mass of the atom. Okay, so neutrons and protons is what's going to give you the mass of the atom, how much the nucleus weighs. So electrons don't weigh. I mean, they do weigh something, but we don't measure the mass of electrons. And so the mass is really coming from the nucleus. So the neutrons plus the protons is going to give you the mass. You can change the mass of an atom without changing the identification of the element. For example, many of you are familiar with carbon. So carbon might be carbon 12, which means it has 6 protons, 6 neutrons. Okay? But we can add a neutron to it. So we could have 7 neutrons and 6 protons, making it carbon 13. Okay? A less stable atom, but nonetheless, the mass is increased. Okay? But the identification or the element itself, it's still carbon. Okay? And this is how we get isotopes of different atoms, is by adding or subtracting the number of neutrons. Okay? Molecules, on the other hand, molecules are just the combination of atoms. Okay? So when atoms bond together, they bond together by sharing electrons. Sometimes these bonds are not, it's not a clean sharing, it's a polar sharing, meaning that one atom pulls the electrons closer to them. For example, in water, okay, oxygen is pulling the electrons that it shares with these two hydrogens. It's pulling it closer to them. So this side of the molecule has a more negative pole, or more negative charge, and this side over here has a more positive charge. Okay, and so we call these polar covalent bonds. Okay, they're sharing electrons, but they're not sharing them equally. Non-polar covalent bonds means there's no charge, and everything is shared equally. In this case, this is methane. Okay, carbon and 4 hydrogen. Okay, and you get this equal sharing, no polarity, no charge on either side. And then you can have, in the case of things like oxygen, the oxygen we breathe, it's a double bond, so it's sharing 2 electrons between the two. Okay, pretty simple stuff. Okay. All right, we're going to finish up. We're going to talk about this experiment that was done by Joseph Priestley, and his experiment kind of followed the same ideas as some of the early researchers, and these experiments have been manipulated and done multiple times by many different researchers for many different reasons. Okay, in some cases they were seeing our plants bringing in carbon dioxide and producing oxygen. In other cases, they're looking at what's the effect of a closed system, etc. And so Joseph Priestley was fairly famous. He was a chemist, published over 150 articles, scientific articles, right? And he really was one of the first to discover molecules and the combination of electrons and the role at which plants play in the production of oxygen. So his classic experiment was to take things like mice and stick them in a chamber with a candle and leave that candle lit. That candle, he hypothesized, was producing carbon dioxide, and over time it was utilizing oxygen to burn, producing carbon dioxide, and the carbon dioxide would get so much in the atmosphere and the oxygen would be depleted that the mouse would die. Then he could do the same experiment except for add a plant to it and see if, again, that plant was able to produce enough oxygen that the mouse didn't die. So again, this was just getting at that connection between oxygen, carbon dioxide, plants, and in this case, mammals. Okay? And so again, the experiment was completed. He did this experiment and then he added the plant. The mouse lived much longer. Now in some cases the mouse still died because there just wasn't enough carbon dioxide for the plant to absorb and transfer and kick out oxygen. And so eventually the carbon dioxide and the oxygen are basically used up, and there's just not enough of either in the atmosphere, and the organism will die anyways. But knowing that the plant produces oxygen, Joseph Priestley realized that this was contributing to life on this planet, that the plants are producing an atmosphere that allows for organisms to live on this planet. Okay, so let's cover a little bit more about Priestley, just his experiments real quick. So he discovered the presence of oxygen molecules in the air. So that early research really dove into the presence of oxygen. And then from that, early research suggested that oxygen was much higher in composition on the planet than what it really is. And it really just took advanced technology and a little bit more experimental analysis to figure out what the actual composition of the air is. But we now know the air is comprised of 78% nitrogen. Okay, and this is current times. Okay, we know that prehistoric times, nitrogen was much higher based on the amount of lightning storms and things like that were occurring on the planet. We can see results from this in rocks and whatnot. And the fact that oxygen was much lower, now it's 21%. Okay? So nitrogen and oxygen, that's 99% of the atmosphere. Okay? So when we're talking about global climate change, people are often thinking, well, carbon dioxide, there's not much carbon dioxide anyways, and there's not. It's only 0.03%. But any little change in carbon dioxide can be drastic enough because there's not much carbon dioxide on the planet. Okay? That 99% of the material on the planet are these two gases. Okay? You start changing the other gases. Okay? You start changing how much water there is, okay? How much carbon dioxide there is. Then you can start getting big changes in the planet. We know that if you change the amount of oxygen that's available, that you can get drastic changes. Okay, just hike up a extremely high mountain, and you'll figure out that the amount of oxygen that's dissolved is decreasing, and so it's harder to breathe. It's harder for you to function. Okay? Same thing with carbon dioxide. You increase it, okay? You change the functionality of the planet. Same thing with water. You decrease it, you change how the planet functions. Okay? And then we know that there's other small gases that are available in the atmosphere at different amounts. Okay? But these are the four big players that make up the majority of the atmosphere. Okay? And so those four are really what we often concentrate on in environmental science. We concentrate on what's the nitrogen level, what's the oxygen level, water, carbon dioxide, and the cycles. Okay? The cycles for all three of these, how are they cycling around? Normally oxygen and water are typically combined in a cycle, but it can also be combined with carbon dioxide. Right? But again, that's why we often talk about these cycles: nitrogen, carbon cycle, and then we'll talk about some other cycles like phosphorus and phosphate, because they're really important for plant growth. Okay. Next time we're going to talk about what makes or what gives the energy in order to do that work. Remember, energy is the ability to do work. Well, where's that energy come from? In a molecule. So when we're talking about carbon dioxide or water or oxygen or nitrogen, where's the energy, right, in that molecule?